So today we're going to be solving the October-November 2024 AS and A-Level Chemistry Paper 1, Variant 1. Question number 1. In this question, Q is used to represent a halogen atom. So Q must refer to atoms in group 17. Magnesium and calcium each form a compound with chlorine and with bromine. One of these compounds contains the element in group 2 with the higher first ionization energy and the element in group 17 with the higher QQ bond energy. So our magnesium and our calcium are both part of our group 2, and our our chlorine and bromine are both a part of group 17. So out of magnesium and calcium, we need to determine the one with the higher first ionization energy. So this is the periodic table for group 2, and well, as you can see, magnesium is above calcium. And as you go down the group 2, our shielding increases. So this isn't exactly how it works, but just for explanation purposes. And however, the proton number does increase, but that's negligible when we're going down the group because the shielding has a much larger impact on the way these atoms react. Now, as the shielding increases, the electrons, or the outer electrons, become further away from the nucleus. Now, the ionization energy refers to the energy needed to remove outer electrons. The more shielding, the further away the electrons, the less energy you need to actually remove the outer electrons. So, magnesium is going to have a higher first ionization energy. So you can already cancel out C and D. Now, what we have to do next is we need to determine which of our group 17 elements has a higher QQ bond energy, and our Q is our halogen atom, so either ClCl or BrBr. As you can see, in group 17, Cl is above Br. And there are a couple of trends that contribute to the bond energy in the molecules or the diatomic molecules formed by group 17. As you go down the group, the bond length increases. The bigger the bond length, the less energy needed to break them apart. Another property down group 17 is shielding again. What this means is as you go down the group, the atom size increases. The larger the atom size, the weaker the attraction to the electron-dense bond. Cl is actually going to be smaller. It's going to give a shorter bond length, so it's going to require more energy to break the bond formed between Cl. So we have our Mg and we have our Cl. That will form an MgCl2 compound. Question number 2. Compound X contains two elements, Y and Z. Element Y is in period 2. In one atom of element Y, the p subshell has all three orbitals occupied, only one is fully occupied. Element Z is in period 3, and in one atom of element Z, the p subshell has only two orbitals occupied. So here are periods 2 and 3, and since we're talking about p subshells, we'll look at the p block of the periodic table. The p subshell has 3 orbitals. We fill electrons singly first, and then we pair them. So it'll go like this, 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 until they are full. Now, for element Y, it says the p subshell
has all 3 orbitals occupied.
And it says only one is fully occupied. So one has 2 electrons. An orbital can only carry 2 electrons max. So what this means is this element has an electron configuration ending in 3p4. Boron is 3p1, carbon is 3p2, nitrogen is 3p3, and oxygen is 3p4. Element Y is definitely oxygen, so we can definitely cross off B and A. Now for element Z, it says the p subshell only has 2 orbitals that are occupied. So Z has the following setup, meaning our Z element ends in 3p2. That would be silicon. Our compound is silicon dioxide. Question number 3. Glauber's salt consists of crystals of hydrated sodium sulfate with the following formula, which can be used for the manufacture of detergents. When a sample of Glauber's salt was heated, 1.91 grams of water was removed, leaving 1.51 grams of anhydrous sodium sulfate. What is the value of X? So for this sort of question, whenever we're trying to calculate, we need to basically understand what is going on here. So what we've done is we've taken our crystallized salt and we've applied heat. This is our Na2SO4.XH2O. After this heat is gone, we are left with Na2SO4. The Na2SO4 is equal to 1.51 grams. When we have water missing, we refer to this as anhydrous. And it says here that 1.91 grams of water was removed. The grams of H2O equaled 1.91 grams. So you can consider for there to be 1 sodium sulfate and X H2O. So it's almost like a molar ratio. First, we're going to find the grams for each. So sodium sulfate has 1.51 grams. H2O has 1.91 grams. We're going to want to find the MR for each. So up here, I've just given the MRs of the elements. You can find these at the back in the periodic table. They'll always be the larger number. So now what we're going to do is we're going to calculate the MR of sodium sulfate. So what we have is we have 2 sodium, so 223, plus 1 sulfur, so 32.1, plus 4 oxygen, which is 16. Type that into our calculators, equals 142.1. So down here, 142.1. To calculate the MR of H2O, it's equal to 2 times 1 plus 16, which equals 18. Now, if we're going to calculate the moles represented by N is equal to the mass in grams divided by the MR. 1.51 divide 142.1 equal to 0.0106. Then we want to find the smallest ratio. So what we're going to do is we're going to divide, and that will give us 1 and 10. So what that means is the molar ratio of sodium sulfate to water is 1 to 10, thus X must equal 10. So our answer is actually going to be C. Question 4. What contains the greatest number of the named particles? So first thing, before we start, something that's really important to know is that 1 mole contains 6.022 times 10 to the 23 particles. So it says 6 decimeters cubed of argon atoms at room conditions. Any gas of 24 decimeters cubed is 1 mole of that gas. So 6 decimeters cubed, 0.25 moles. Then it says 6 carbons of carbon dioxide molecules. The formula for carbon dioxide is CO2. So the MR of CO2 equals 12 plus 2 times 16, which equals 44. Moles equals mass in grams over MR, which equals to 6 over 44, which is equal to 0.136 moles. Now what it says is 6 grams of magnesium atoms. The MR of magnesium is equal to 24.3. 6 over 24.3 gives you 0.247 moles. Last one is 6 grams of water. Water has the formula H2O. MR of H2O is equal to 2 times 1 plus 16, which equals 18. So the moles of H2O is equal to 6 divided 18, which equals 0.33 occurring moles. Therefore, the correct answer is going to be D. Now, the reason why I didn't go and calculate the number of particles, I could have, if I wanted to, by simply multiplying N, the number of moles, by 6.022 times 10 to the power 23. But I don't have to do this for this question because the number of moles is equivalent to the number of particles. So you don't actually have to go through the extra effort of doing so. Question number 5. Phosphorus forms a compound with hydrogen called phosphine, which has the formula pH3. This compound can react with a hydrogen ion. Which type of interaction occurs between a pH3 and a hydrogen ion? So first of all, I think we should start with drawing out our pH3 molecule to determine how many bonding pairs and how many lone pairs there are. Phosphorus is in group 15, so it has 5 outer electrons. There are 3 hydrogen atoms, 8 outer electrons in total. Divide this number by 2. So 8 divided 2, there's 4 electron pairs. Since we have 3 hydrogen atoms, there must be 3 bonding pairs and 1 lone pair. I expect this to take place, where an electron pair is coming from P. That is because a hydrogen ion actually has no electrons to share. That's because hydrogen only has 1 outer electron, and a hydrogen plus ion has lost an electron. So it actually has 0 outer electrons. So it must receive all its electrons from phosphorus. This must mean that the type of interaction that occurs between pH3 and a hydrogen ion is actually a dative covalent bond. And that is when the electron pair is coming from 1 atom and not being shared. Question number 6. The graphs show trends in 4 physical properties of elements in period 3. Which graph has electronegativity on the y-axis? So what is electronegativity? It's the tendency of an atom to attract the electron pair in a covalent bond. So take HCl for example. We know that Cl is actually more electronegative than H. So actually it attracts the electrons in the covalent bond more than the hydrogen. So the electrons sort of are closer to the Cl. This makes Cl delta negative and H delta positive. Let's imagine this is our period 3. As you go across the group, you're going to have similar shielding throughout, but it's also increasing in atomic number. The nuclei are more positive, so they will more strongly attract electrons, and thus they will have a greater tendency to attract the electrons in the covalent bond. So our graph should be increasing all the way throughout our period 3. We can cross off A because there's an increase, then a decrease, not a consistent increase throughout. B is simply just a decrease, so that's the opposite. C, there are decreases at certain points, so we can exclude that. And D is our correct answer. Now, the other graphs can represent other things. So I think for B, we're probably referring to the radii, perhaps. In C, we're probably talking about ionization energy. A is probably talking about the melting point of oxides. Question number 7. The element tin exists in 2 forms, grey and white tin. Some properties of grey tin and white tin are shown down below the table, and it asks us which structural change might take place when grey tin changes to white tin. And our options consist of different types of structures: giant ionic, giant covalent, and giant metallic. So let's take a look at our table. Grey tin's boiling point is 2543 Kelvin. White tin is 2533 Kelvin. So as you can see, there isn't much of a difference in their boiling points. It's around a 10 Kelvin difference, but they're both very high. Electrical conductivity. So grey tin is not conductive in solid or liquid, so it's simply just an insulator. And white tin is good in both solid and liquid. In terms of malleability, grey tin is brittle, while white tin is malleable. So I think we can't really do much based off of boiling points because they're both very high and similar. But in terms of electrical conductivity, grey tin doesn't conduct whatsoever. White tin does in both solid and liquid. From this, I can tell you that grey tin is definitely a giant covalent. Now, the reason for this is giant covalent structures are non-conductors. Ionic lattices conduct when molten, which is basically when they are in their liquid form. White tin is a good conductor in both liquid and in solid, so it must be metallic. And to confirm, when we look at our malleability, grey tin is brittle while white tin is malleable. Now, malleability is a property of metallic substances. Okay, so it's asking us what has a simple molecular lattice. Calcium is a metal, fluorine is a non-metal. A metal and a non-metal give us an ionic compound. Now, B, nickel is actually a metal, definitely not simple molecular. C, silicon oxide. This is a known example of a giant covalent. So our answer must be D, sulfur. Question number 9. The standard enthalpy change of combustion of carbon is negative 394 kilojoules per mole. The standard enthalpy change of combustion of hydrogen is negative 286 kilojoules per mole. The standard enthalpy change of formation of butane is negative 129 kilojoules per mole. What is the standard enthalpy change of combustion of butane? So butane is an alkane. We're trying to determine the enthalpy change of combustion. So when C4H10 completely combusts with oxygen, or when any hydrocarbon completely combusts, we form a set mole of CO2 and a set mole of H2O. 4 carbons in butane, we need 4 moles of carbon dioxide, and since we have 10 moles of hydrogen per butane molecule, we must add 5 here. 4 times 2 oxygen here, and 5 oxygen here. And we have 5 oxygen here. So on this side, the number of oxygen is equal to 8 plus 5, which is 13. So we have 13 divided 2. Now, it's asking for the enthalpy change of combustion, and we only have 1 mole of butane, so it's just negative 129. Now, the enthalpy change of combustion of carbon is negative 394, and for hydrogen, it's negative 286. We're going to have 4 times negative 394. 5 moles of water. So that's 5 times minus 286. The reason why we didn't use 10 is because we have been given the combustion of hydrogen. Hydrogen has 2 hydrogen atoms, so all these have been made from C, from H2, from O2. Okay? Now, to find the enthalpy change, you have to do the enthalpy of the products minus the enthalpy of the reactants. 4 times negative 394 plus 5 negative 286 minus negative 129. You get negative 2,877 kilojoules per mole. The answer thus is B. Question number 10. 3 processes are described, and we have been given 3 equations. It's asked us which statement is correct. Either one of the 3 processes has a positive enthalpy change, and which one, or whether they all have negative enthalpy changes. Now, something that is important to note is the fact that any negative enthalpy change means an equation is exothermic. In the first equation, hydrogen ions react with hydroxide ions to form water. So what is happening is a bond is being made. So bond making is exo. You may or may not have heard of this, but we use bendomax to remember that endo reactions are breaking of bonds, and exothermic reactions involve making bonds. And here a bond is being made, so it's definitely not B because it has a negative enthalpy change. The second reaction is a combustion reaction. We know that it is because we have O2 reacting with a substance, and CO2 and H2O are being formed. Combustion reactions are exothermic because they actually release heat. So we know for a fact it is not C because reaction number 2 is exothermic. The last equation shows a gas becoming a liquid. So reaction 3 must show a condensation reaction. A condensation reaction releases energy. In a gas, you have very far apart molecules traveling at high speed, but when you reduce the temperature, they start to move closer together and at a lower energy because that energy has actually been distributed to its surroundings. So the correct answer is A. Question number 11. In alkaline solution, MnO4- ions oxidize SO3 2- ions to SO4 2- ions the MnO4 minus ions are reduced to MnO2. What is the ratio of the two ions in the balanced chemical equation for this reaction? Now, before we combine the two reactions, we want to produce single reactions for the reduction of MnO4 minus ions and the oxidation of SO32 minus ions, and then combine them. Pay attention to the fact that this is alkaline solution. So what I like to do is I like to balance it as if it's acidic, and then add hydroxide ions on either side at the end. So MnO4 minus 2 MnO2. As you can see, we lack two oxygens on this side, so we're going to add 2 H2O. And now we're missing 4 hydrogens on this side, so we're going to add 4H+. Now on this side we have an overall charge of 3, because there are 4 positives and 1 negative, and we have a charge of 0. So to balance out this positive charge, we're going to add 3 electrons on this side. Now to turn this into an alkaline solution, remember we won't have hydrogen ions, that will only be present in an acidic solution. We're going to add hydroxide ions to each hydrogen ion. So, and we have to add the same number of hydroxide ions on either side to ensure we are being fair, we're not changing the actual equation. So 4 hydrogen ions on here, we're going to add 4 OH minus here and 4 OH minus here. This is going to give us 4 H2O, so we end up with this. However, we have water on both sides, so what we can do is we can cancel out the 2 on this side and just make this 2. Let's write the free equation for oxidation of SO32 minus ions. However, as you can see, we can't really directly combine the two equations because there's 3 electrons up here and 2 electrons down here. So before we can combine the two, we're going to have to multiply this by 2 and multiply this by 3. 2 MnO4 minus to 3 SO32 minus 2. And the answer, therefore, is A. Question number 12. Lithium reacts with nitrogen at room temperature to form the solid with the following formula. 3 vessels of equal volumes are connected by taps 1 and 2. At the start, taps 1 and 2 are closed. The left-hand vessel is evacuated. The middle vessel has the indicated reaction at equilibrium, and the right-hand vessel contains lithium only. Which action would allow the equilibrium mixture to contain the most ammonia? Now for this question, you have to understand what these taps will do when opened and when closed, using the principle of volume and pressure changes and how they impact each other. Volume and pressure are inversely proportional. So if you have a small volume, you're going to have lots of pressure, and if you have a large volume, you're going to have small pressure. So when you open the tap, you get volume increase because now you have all of this. If we open tap 1, you'll have all of this, and thus the pressure is going to decrease. If the pressure decreases, the equilibrium is going to shift to the left, to the side with more moles, because we have 4 moles in total on this side and only 2 on this side, to increase that pressure once again, so we won't end up with as much ammonia. Now, what happens if we only open tap 2? Not only will we also have less ammonia, we'll have much less ammonia because some of the nitrogen is actually going to flow into here, and it's going to react with the lithium, and it's going to give us lithium 3N. And what that means is there's going to be fewer nitrogen reacting molecules to react with hydrogen to form ammonia. This will also mean fewer successful collisions because we have fewer reactants per unit volume. If we open both taps 1 and 2, we're going to have triple that effect because we have less nitrogen, the lowest amount of pressure possible because we have the highest amount of volume present. So the answer must be A. Question number 13. When 0.2 moles of hydrogen gas and 0.15 moles of iodine gas are heated at 723 Kelvin until equilibrium is established, the equilibrium mixture contains 0.26 moles of hydrogen iodide. It's given us the equation for the reaction, and it's asked us to give the correct expression for Kc. Kc equation for this as follows. It's always product on top, and any moles are used as powers. Moles, powers, and products over reactants. We also need to know something, and that is Kc only uses the number of moles at equilibrium, or the concentrations at equilibrium. So where is the volume? We all know that concentration is equal to moles over volume. But we don't have a volume. Why? Well, because we don't need to, because the powers actually cancel out. So we don't write this, but H2 is actually raised to the power of 1, and so is iodine. Now, if you add the two powers on the bottom, we actually get 2 over 2, and that just gives us 1. So actually, the volumes will end up cancelling out because they are equal. So you don't actually need the volume in this case. Now, let's figure out the number of moles at equilibrium. So I'm just going to rewrite the equation, and we're going to use ice. I stands for initial, C, change, and E, equilibrium. At first, we have 0.2 moles of hydrogen. Then we have 0.15 moles of iodine. And we'll have none because it's just started and we don't have any hydrogen iodide to begin with. However, it says here that we have 0.26 moles of hydrogen iodide at equilibrium. So the change, or the difference, must have been 0.26 moles from 0 moles for hydrogen iodide. Now the molar ratios are 1 to 1 to 2. So the change for iodine and hydrogen will be half of that. 0.26 divided by 2 is actually 0.13. Change is 0.13 and 0.13. There was an increase here of the number of products, so there must have been a decrease for the number of reactants. So 0.15 minus 0.13 is 0.02, and 0.2 minus 0.13 is 0.07. And then when we take these and we plug them in to our Kc, we're going to end up with option C. In A and B, they multiply by 2, and that's a common mistake. That's incorrect, because the moles form the powers. In D, they must have used the difference and not the actual number of moles at equilibrium. Question number 14. In acidic conditions, iodine reacts with propene in a substitution reaction. The equation for the reaction is as follows. The kinetics of the reaction are investigated using a colorimeter. As the iodine reacts, the yellow-brown color of iodine fades to colorless, changing the absorbance of the solution. Known concentrations of iodine are used to prepare a calibration curve graph, and the absorbance is then measured as the reaction proceeds. So the iodine is yellow-brown, and then it turns to colorless. We are measuring the reaction as it proceeds, so it is a continuous reaction rate practical, and we are given two graphs. They've asked us to find the rate of the reaction at 20 seconds. Now, there are several measures of reaction rates, and one of the measures of reaction rates is the concentration of reactants used up over the time taken to use them up. So what we need to do is we need to find the initial concentration of iodine, so at 0 seconds. And then we need to find the concentration of iodine at 20 seconds and subtract them to find the amount used up during this time. So at 0 seconds, we have a 0.5 absorbance. That gives us a concentration of 0.25 times 10 to the negative 3 moles per decimeter cubed. And at 20 seconds, we have an absorbance of 0.3. So that gives us a concentration of 0.15 times 10 to the negative 3 moles per decimeter cubed. So the amount used up equals 0.25 minus 0.15 times 10 to the negative 3, which equals 0.1 times 10 to the negative 3. Now we have to divide that by the time. So 0.1 times 10 to the negative 3 divide 20 seconds. That will give us 5 times 10 to the negative 6. So our answer is A. And just to make sure, we look at our units. So it is moles per decimeter cubed per second. Now, in terms of the principles behind absorption, you don't really need to know much for this reaction. But as you can see, as the concentration of iodine increases, the absorbance also increases. That is because colored solutions absorb a lot better than colorless solutions. Question number 15. The diagram shows a Boltzmann distribution curve. The axes are not labeled. Points X and Y are on the vertical axis. What is represented by both? Okay, so we're given a few options, but before we start, let's label our axes. So our x-axis actually represents energy, and a y-axis represents the number of molecules or particles at the given energy. Here, EA stands for the activation energy, and it is the minimum amount of energy needed for a successful collision to occur. At this point where it peaks, this is actually considered the most probable energy, and it is the energy that most particles have. At the origin, 0 particles have 0 energy, and at the end, it never reaches E0 because there is no such thing as a particle that lacks energy. We're going to start from the bottom, and then we're going to work our way upwards. So let's take a look at D. So point X right here is the number of molecules with energy equal to or greater than EA. So it's actually the number equal to, not the number greater than, because we're only looking at one point, and that's on the activation energy. Point Y, the amount of energy of the greatest number of molecules. Now, while this sounds right, point Y actually refers to the number of molecules at this given energy. And while this energy is the amount of energy of the greatest number of molecules, because we're pointing at the point on the curve and not on the x-axis, we're not actually referring to the energy at this point. So that would be incorrect. This C would be correct, and this would be incorrect. Again, this is incorrect, and this would be correct because this is the largest number of molecules with the same energy. That must mean that our answer is A. Question 16. What are the acid-base nature and structure of sulfur dioxide? So first of all, sulfur dioxide has the following structure. It is simple molecular, and it is actually acidic. So the answer must be B. It's acidic because SO2 can actually react with water to form an acid called sulfurous acid. Question number 17. Elements X and Y are in period 3 of the periodic table. Element X is either phosphorus or sulfur. Element Y is either sodium or magnesium. Element X forms an oxide with water when it reacts with water to give a solution containing the aqueous anion XO42-. 1 mole of element Y reacts with 1 mole of chlorine molecules. At the end of the reaction, all of the element of Y and all of the chlorine have been used up. What are the elements X and Y? So let's take a look at element X first. So you've been told it's either phosphorus or sulfur. Now, we need to be familiar with the types of oxides that period 3 elements make. And we know for a fact that phosphorus makes this anion, sulfur makes this anion. So we know that since the charge is 2-, that means our element X must be sulfur, not A or B. If we look at element Y, it says element Y reacts with 1 mole of chlorine molecules, and at the end all the chlorine molecules have been used up. So let's react sodium with chlorine and magnesium with chlorine. So if we do Mg plus Cl2, and they have to be 1 mole each, we will get MgCl2. If we react sodium with chlorine, we will get NaCl. That is because Mg is in group 2, sodium is in group 1. So magnesium requires 2 chlorine atoms per magnesium, while sodium only requires 1. If you take a look, there's 1 mole here, 1 mole here. This equation actually doesn't balance. So it must mean that not all of the chlorine molecules have been used up. Therefore, element Y must be magnesium, and so our answer is D. Question number 18. Q is a semiconductor. The chloride of Q reacts with water to form white fumes and an acidic solution. Which period 3 element is Q? So first of all, the fact that it is a conductor means that it has some metallic properties. We can exclude D because phosphorus is not metallic. Silicone is a metalloid, so it does have some metallic properties. Then it says that there are white fumes produced, and because we have Cl chloride involved, then the white fumes are probably from HCl gas. When aluminium, however, reacts with water, when aluminium chloride reacts with water, no HCl is produced, so we can cross off B. Then it says the solution is acidic. Now, the only period 3 elements that can form acidic solutions would be aluminium, phosphorus, silicone, and sulfur. Therefore, A is also wrong because magnesium chloride which react with water to form a basic solution, so the answer must be C. Question number 19. V and W are two compounds, each one contains a different group 2 element. A sample of each solid is added to water, shaken, and the pH of the resulting solution is measured. So here is a table, and it has compounds V and W and the pHs of each one. Which row could identify V and W? First of all, both of these pHs are greater than 7, so that means they must be basic solutions. So I can already cross off A and B. That is because barium sulfate and magnesium sulfate are actually salts and not bases, so they would have a pH of 7. They are neutral. The answer must either be C or D. Now, if we compare barium hydroxide and magnesium hydroxide, we know that magnesium is actually above barium in the periodic table in group 2. As you go down the group, hydroxides become more soluble. So therefore, barium hydroxide is going to be a lot more soluble than magnesium hydroxide. And therefore, it will dissociate more hydroxide ions, which will result in a higher pH solution because it will be more basic. Therefore, our answer must be C. Question number 20. Compound L decomposes on heating. One of the products is gas M. M reacts with unburned hydrocarbons to form peroxyacetyl nitrate, PAN. What could be the formula of L? So hydrocarbons consist of C and H atoms only, and we know that M has reacted to produce something that contains nitrate. So we're going to presume that compound L actually contains nitrate ions for it to be able to end up in PAN. So that means we can cross off C and D. Now, the difference between the A and B is the fact that we have 2 nitrates for calcium in B and 1 nitrate for calcium in A. Nitrate ions have a 1- charge, and calcium ions have a 2+ charge. And for the compound to have an overall charge of 0, we're going to need 2 nitrate ions. So for each calcium ion, that must mean that our answer is B. Now, at A level, there is more to it. What was the gas produced that reacted with the unburned hydrocarbons? That gas must have been nitrogen dioxide, because that is produced from the decomposition of group 2 nitrates. And the equation that actually takes place is as follows. So calcium nitrate decomposes via heating to form calcium oxide plus 2 nitrogen dioxide plus half oxygen. And you must have this setup memorized. And so as you can see, this is the nitrogen dioxide produced, and this is what reacts. Question number 21. In reaction 1, concentrated sulfuric acid is added to potassium chloride, and fumes are produced and are bubbled into aqueous potassium iodide solution. In reaction 2, potassium chloride is dissolved in aqueous ammonia and then added to aqueous silver nitrate. So what is potassium chloride? That is KCl, and it is added to H2SO4. The reaction that occurs in reaction 1 is H2SO4 reacts with KCl to produce HCl plus NaHSO4. HCl is a gas and it produces white fumes, the one we're referring to here. It says they are then bubbled, and then this solution is then bubbled into potassium iodide solution. HCl plus potassium iodide is actually not going to produce anything, so no reaction. Both HCl and Ki are colorless, and no reaction takes place. That is because Cl is more reactive than iodide, so iodide cannot displace it. So in reaction 2, when KCl is dissolved in ammonia, it says the resulting solution is then added to silver nitrate, and the reaction between these two reactions actually forms an aliphatic amine and an ammonium salt. Now, silver nitrate is usually used to test for the presence of chloride, bromide, and iodide ions, and while you would expect for there to be a color change with NH4Cl because it contains chloride ions, AgCl actually is not produced, so we don't have a white precipitate. We can cross off D, and the answer must be C. Question 22. The table refers to the hydrogen halides. Which row is correct? Something that is very important to know is the fact that the hydrogen halides stability increases as you go up the group. That being said, HCl is more stable than HBr. Therefore, it is easier to oxidize HBr than it is to oxidize HCl. And there is less heat needed to break the bond between HBr than HCl. Therefore, the thermal stability of hydrogen halides as you go down the group decreases. So the answer must be C. Question number 23. 7.5 grams of nitrogen monoxide reacts with 7 grams of carbon monoxide on the surface of a catalytic converter in the exhaust system of a car. What is the total volume of the product gases measured at room conditions? So the reaction for nitrogen monoxide with carbon monoxide is as follows. So it's 2 nitrogen monoxide, 2 carbon monoxide to give 2 CO2 plus N2. So what we need to do is we need to find the moles of nitrogen monoxide. First off, we find the MR of nitrogen monoxide, and that is 14 plus 16, which equals 30. And the MR of carbon monoxide, which is 12 plus 16, which equals 28. To find the moles of nitrogen monoxide, we know that moles equal mass in grams, divide MR. So the moles of nitrogen monoxide is 7.5 divided 30, which equals 0.25. And the moles of carbon monoxide equals 7 grams divided 28, which also equals 0.25 moles. Since we have equal number of moles and the ratio of nitrogen monoxide to carbon monoxide is 1 to 1, there are no limiting reagents, so we can use either or. So the ratio of carbon monoxide to carbon dioxide to nitrogen is 2 to 2 to 1. Therefore, the moles of carbon dioxide produced is equal to 0.25, and the moles of nitrogen is equal to 0.25 divided by 2, which equals 0.125. In total, we have 0.375 moles. 0.375 moles is equal to something decimeters. 1 mole equals 24 decimeters cubed. So by cross multiplication, we get the number of decimeters cubed, or the volume, is equal to 0.375 times 24, which gives us 9 decimeters cubed. So the answer must be C. Question 24. 3 statements about ammonia molecules and ammonium ions are given. Which statements are correct? So let's take a look at each statement. In aqueous solution, ammonia molecules form coordinate bonds with hydroxide ions. So what happens when ammonia is in aqueous solution? We actually get NH4OH. Now, this is not a coordinate bond. The hydroxide ion has a minus charge and the NH4 ion has a positive charge. And together they form an overall compound with 0 charge. So that's not the case, because this is how a coordinate bond works, where the ammonia, for example, donates a electron pair to form a dative covalent bond with another atom. Now, in this case, the NH4 plus involves a dative bond, but it doesn't form a dative bond with the OH minus ion. So 1A, B, and D are definitely incorrect. But let's just take a look at the 2 other statements. Ammonium ions are Bronsted-Lowry acids. So what is a Bronsted-Lowry acid? It is defined as something or a species that is a proton donor. Ammonium ions, as we have just looked at, actually have a positive charge. So they are more likely to want to lose this hydrogen atom. So what they can do is they can actually donate one of their hydrogens. So yes, this is the case for ammonium ions. In statement number 3, it says that the H-NH bond angle is larger in the ammonium ion than it is in ammonia. So let's take a look at both. In the ion, which is NH4+, this is what it looks like. And it has a bond angle of 109.5. As ammonia, it'll have 1 lone pair. So we actually get a bond angle of 107 degrees. there is a minus 2.5 degree difference in the bond angles because lone pair repulsion is actually greater than bond pair repulsion. So for this very reason, the bond angle in ammonium ions is greater than the bond angle in ammonia. Therefore, the answer is C. Ethene reacts with steam in the presence of sulfuric acid. What type of reaction is this? So from the name ethene, we can tell using the suffix that this is an alkene. Alkenes undergo electrophilic addition. So the answer must be B. Question number 26. Compound Z has a molecular formula C4H8O2. Compound Z reacts with propanol in the presence of concentrated sulfuric acid. The diagram shows the skeletal formula of 3 compounds. What are the possible skeletal formulae of the products of the reaction between compound Z and propan-1-ol? So if we take a look at our 3 skeletal structures, we can see that they are all esters. That is because an alcohol has reacted with a carboxylic acid. Now the carboxylic acid contains 4 carbons, and propan-1-ol is an alcohol that contains 3 carbons. So our ester should have a total of 7 carbons. Now remember, the vertices of each line on a skeletal formula represents a carbon molecule or carbon atom bonded to other H's. So there in S there's 1, 2, 3, 4, 5, 6, so it can't be S. In T there's 1, 2, 3, 4, 5, 6, 7, so it can be T. And in U there's 1, 2, 3, 4, 5, 6, 7, 8, so it can't be U. Therefore the answer must be D. Question number 27. Geraniol and nerol are isomers of each other. Which type of isomerism is shown here? So our first option is chain isomerism. Now there isn't any chain isomerism because there isn't any branching differences in either of the isomers. So it's definitely not A. Now the second option is geometrical cis/trans isomerism. If we look at our 2 alkenes, we can see here in this one, there is no cis-trans isomerism because we have 2 of the same methyl groups attached to one of the carbons, so there's none here. Here we have 2 different groups here, so there is a possibility for cis-trans isomerism. And so if we look at that same carbon-carbon double bond on here, you can see that there has been a switch. It has gone from cis to trans, because now the CH3 and CH2OH, so the heavier molecular mass groups, are now on the opposite sides. So the answer must be B. However, let's take a look at all the other options. We know that there isn't any optical isomerism because there's not a single carbon with 4 different groups attached to it. And if you look around at each single carbon, you will find that there isn't. And it isn't positional because none of the carbons have, or none of the functional groups, like OH here, has moved around. It's stayed in the same place. Question 28. Which compound has the greatest number of stereoisomers? So there are 2 types. There's optical stereoisomerism and there's EZ stereoisomerism, also known as cis-trans isomerism. Now I have drawn out the structures of the options A to D just to save time. And as you can see, in A we have no sort of stereoisomerism because there are 2 of the same groups attached to the carbon-carbon double bond, so there isn't even EZ isomerism. There's no optical isomerism because there's not a single carbon atom with 4 different groups bound to it. B and D both show cis-trans isomerism only, and C actually shows optical isomerism using this chiral carbon, but cis-trans isomerism as well because these 2 are different and these 2 are different. So the answer must be C. Question 29. Vitamin A contains retinol, and this is the structure for that retinol. Under appropriate conditions, acidified potassium dichromate can be used to break C-C double bonds. After these bonds have been broken, further oxidation can occur. What conditions are needed for the acidified potassium dichromate used, and what do the final oxidation products include? So as you can see, we have some carbon-carbon double bonds, and the conditions that we require to be able to break these carbon-carbon double bonds is the potassium dichromate must be hot and concentrated. Now what we will end up getting is we're going to have these carbon-carbon double bonds be replaced by OH groups. Now at the end of this structure we actually have an OH group. This can be oxidized to an aldehyde and then to a carboxylic acid, while the OHs here can only be oxidized to ketone groups. Therefore, we end up with the answer being D. Now, because further oxidation occurs, the aldehydes don't remain and they actually undergo this transformation. Question number 30. The structure of limonene is shown. What are the number of moles of carbon dioxide and water produced when a sample of limonene is completely combusted in oxygen? So in complete combustion, CO2 and H2O are the only products. If we look at the limonene structure, we can count the number of carbons and hydrogens. So if we first start off with the number of carbons, we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 carbons, and we can count the number of hydrogens. So there are 3 here, there's 1 here, there is 2 here, there is 2 here, 2 here. There is 1 here, there is 3 here, there is none here, and there is 2 here. If we add them all up, 4 plus 3 is 7, plus 8 plus 10 plus 16. The number of hydrogens equals 16. So what this means is the molecular formula for limonene is C10H16. So C10H16 reacts with a set number of moles of oxygen to produce CO2 and H2O. There are 10 carbons in C10H16, so there are 10 moles of CO2. There are 16 hydrogens, so we add 8 here because 8 times 2 is 16, and that means we would be reacting 14 oxygens. So if we look in our table, we can't actually find any 10 and 8. But what we can see is that CO2 to H2O is in a 10 to 8 molar ratio. We can make this even smaller by dividing by 2. We will be given 5 to 4. And that is the same as option B. So that must be our answer. Question number 31. The reaction of chlorine with methane is carried out in the presence of light. What is the function of the light? So Cl2 in the presence of UV actually causes the Cl-Cl bond to break so that we can form 2 Cl free radicals. So the answer is actually B. Question number 32. When X is added to NaOH and heated under reflux, pentanetol is made. Which organic product is made when X is heated with a solution of KCN? So you might be familiar with this mechanism, but when an alcohol is made from using sodium hydroxide under reflux, then it's likely to have been a nucleophilic substitution from a halogenoalkane. So pentanetol structure looks like this. 1, 2, 3, 4, 5. And the OH is here. But originally, this OH group was replaced by a chlorine atom or a bromine atom. Regardless, when you add KCN under ethanolic conditions, another type of nucleophilic substitution reaction will occur, and the CN will then just replace the Cl group, and you'll end up with D. Question number 33. 1-chlorobutane, 1-iodobutane both react with aqueous sodium hydroxide via a nucleophilic substitution mechanism. Which reaction has the greatest rate under the same conditions, and which mechanism is followed by this reaction? Something that's really important to understand is that as you go down the group, hydrolysis becomes a lot faster. That is because the CCl bond is the strongest and the Ci bond is the weakest. Therefore, it is a lot easier and it requires a lot less energy to break the Ci bond, and so it can undergo nucleophilic substitution at a much faster rate. Secondly, what mechanism follows? The mechanism that follows is going to be SN2, so the answer is going to be D. That is because the substance involved is a primary halogenoalkane. Question number 34. Compound Y reacts with alkaline iodine. When the products of this reaction are acidified, the dicarboxylic acid is produced. The formula of the dicarboxylic acid is as follows, where Al consists of one or more CH2 groups. What is compound Y? So our options are all pentandiols, so pentan is 5, and diol means there are two OH groups. Now this is actually an iodoform reaction. So what happens is in an alcohol, in a secondary alcohol, the alcohol group and the CH3 next to it are removed and replaced with COO minus. So basically, if we have an alcohol here, it's going to become O. Okay? So it's a dialcohol, so a diol, sorry, so we need an OH on this end as well. But it has to be secondary. Therefore, another O is going to form, and there's a minus sign and a minus sign. Since it's acidified, that means there are hydrogen ions present, and then these two will get hydrogen ions added to them to form a dicarboxylic acid. So this is located on carbon 2, this is located on carbon 4, so the answer must be D. Question 35. Which alcohol gives only one possible oxidation product when warmed with acidified potassium dichromate? So we have 4 options. A, C, and D are all primary alcohols. So these alcohols can be oxidized to form aldehydes and then carboxylic acids, while B is a secondary alcohol, so it can only form ketones upon oxidation. Therefore, the answer is B. Question 36. Which compound on reaction with hydrogen cyanide produces a compound with a chiral center? Hydrogen cyanide has a formula HCN. So what I'm going to do is for each compound, I'm going to draw what would form. So for A, we'll get HCN, and the carbon is bonded to 4 different groups. So this carbon has a chiral center, thus the answer must be A. If you try this out with all the other options, you will not get a chiral center, and you will get at least 2 same groups bonded to each carbon. The diagram shows 3 reactions of ethanol. In each case, an excess of ethanol is used. What are the observations made after each of the 3 reactions? What are the colors of solutions 1, solids 2, and 3? So for solution 1, what we did is we added acidified potassium dichromate to ethanol. This is going to oxidize our ethanol to produce COOH. And when oxidation takes place, potassium dichromate is orange, but it will turn green when it is reduced to oxidize the ethanol. So we can already cross off C and D. Now, for solid 2, what we're doing is we're adding alkaline iodine to ethanol. This is an iodoform reaction, and it produces iodoform, which is CHI3, which is a yellow solid. Now, in reaction number 3, solid 3 is produced by adding Fehling solution. Fehling solution is blue, and when an ethanol is oxidized by Fehling solution, red precipitate forms. So the answer must be B. Question 38. 2,2-dimethylbutane nitrile reacts to form alcohol Y via the reaction sequence shown below. Which row names the molecule X and the class of alcohol Y? So I've drawn out the structure to save time. And in reaction 1, we have hydrogen ions, which we can presume are coming from an acid. And so this nitrile is probably undergoing acid hydrolysis. Acid hydrolysis results in the formation of a carboxylic acid. So this CN group is going to turn into a COOH group. So we'll end up with the following acid. COOH. In the second reaction, we have this substance, and this is actually a common reducing agent. It reduces carboxylic acids to alcohols. So instead of redrawing this, we will actually end up with a primary alcohol. That is because this carbon atom is only directly bonded to one other carbon atom. So we can cross off B and D because it's a primary alcohol. And let us name the carboxylic acid that was once produced X. Now this is, so we actually name starting from the functional group. So this is 1, 2, 3, and there are 2 methyl groups. So it's 2,2-dimethyl propanoic acid, but we don't actually have to name the methyl groups here. So the answer is C. Question 39. The diagram shows a section of an addition polymer. The polymer is made using two different monomers. What are the names of the two monomers needed to make this polymer? So it's an additional polymer, meaning it's made from alkenes which contain carbon-carbon double bonds. All the answers seem to consist of alkenes, so that doesn't really help much. Now, looking at the structure of the polymer, you need to find where the unit repeats itself. And if you look carefully, it actually repeats after this point. So this is one repeating unit, and this is another repeating unit. And you can find that actually if you split one of these repeating units here in half, you get the two monomers that make up a single repeating unit. So like I said, it's consisting of alkenes, so there'll be a double bond here and a double bond here. For this one, there's a chlorine on one end and the chlorine right next to it. So if we draw this out, we actually get C, 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 and we get a Cl here and a Cl here and a H here. And if we look at this one, we get CH3 bonded to C, bonded to Cl, C bonded to CH3, and a H here. This right here is 1,2-dichloropropene. This right here is 2-chlorobutadiene. So the answer must be A. Question number 40. The diagram shows the mass spectrum of a sample of chlorine. The peaks V, W, X, Y, and Z are labeled. Which statements about the mass spectrum are correct? Okay, so we're taking a look at chlorine and we have 5 peaks. Okay, something that's important to know about chlorine is the chlorine atom actually has 2 isotopes. It has the 35 and the 37 isotope. The 35 isotope actually makes up 75% of chlorine atoms, and the 37 makes 25% of chlorine atoms. These percentages are referred to as the relative intensity, and you can see that here, down here at 35, and down here at 37, these peaks represent the relative intensities. So V represents the 35 Cl isotope, and W represents the 37 Cl isotopes. We have 3 other isotopes down here. And these are actually for chlorine itself. So Cl2 is just 2 Cl atoms bonded to each other. But there are multiple options that you could have 35 Cl bonded to 35 Cl. You could have 37 Cl bonded to 37 Cl. You could have 35 Cl bonded to 37 Cl. And this represents those peaks. So this will actually give you 70 Cl2. This will give you 74 Cl2, and this will give you 72 Cl2. So X, Y, Z represent these relative intensities. Z would be this would be our Z. Y is at, because Z is at 74, our Y is at 72. This would be our Y, and this would be our X. Let's take a look at our statements. The relative atomic mass of chlorine can be calculated from the abundances of 2 of the 5 peaks. So relative atomic mass refers to the average mass of an atom compared to 1/12 of a carbon-12 atom. So like we mentioned at the beginning, these are the 2 isotopes that form these 2 peaks right here for the chlorine atom and not the chlorine molecule. Remember, this is the chlorine molecule. So this statement is true. Statement number 2. 37 grams of the species responsible for peak Z contain 3.011 times 10 to the power 23 molecules. So species Z is at 74 M. So Me equals 74. 74 is therefore the molecular mass. And we said 37 grams of it. So the number of moles equals the mass in grams over mR, which equals 37 divided 74, which equals 0.5. In 1 mole, you will have 6.022 times 10 to the power 23 molecules. So in 0.5 moles, you will have 3.011 times 10 to the power 23 molecules. Therefore, this statement is also true. Statement number 3 says the relative molecular masses of chlorine can be calculated from the abundances and the Me values of peaks X, Y, and Z. This is true for the molecule of chlorine. Like we mentioned earlier, these 3 peaks can be used. Therefore, all 3 statements are correct, and our answer is A. So to add, because I feel like I haven't clarified enough, to calculate the relative atomic mass, all you do is you do 35 times the percentage abundance plus 37 times the percentage abundance over 100, and that would give you your relative atomic mass, which should result in 35.5.